So what we started discussing last time was a Polyakov path integral. And so I'm just going to very quickly remind what we did so that we won't get lost. So what we were thinking about path integral for string theory as a sum over all possible configuration of worldsheets. And so we have to integrate obviously fields that live on the worldsheet, and we have to integrate over the worldsheet metric. So we have e to the minus s, where s is just a Polyakov action, right? The Polyakov action. So action s, subscript s, 1 over 4 pi, and an integral into sigma over g. Again, remember that we're doing this computation in Euclidean worldsheets. Okay. So I have del x a mu, del a x mu. And then there is an additional term, right? So there is a coupling lambda times the Euler character of the worldsheet. First thing that we were discussing is that as a path integral, so this is a path integral, it's a partition function. You can think for a single string. This is a partition. Single string. We have to be careful is that there is a lot of symmetries on the worldsheet, and so what we have to divide it by a symmetry rule, which is divided by the volume morphism plus the volume also by symmetry rule. And so the way how we were thinking is that so there is a whole space of configurations, right, that we have to integrate over. That space involves x and metric on the worldsheet. And so we focus only on the metrics, right, because those are also degrees of freedom that we have to fix there. And so one way to do it is to identify what are our gauge slices. What we want to do, we want to fix some fiducial metric, which we call g hat, and integrate only along the gauge, along the physical configuration. And so one of the assumptions we made, so we assume, and I think it will be crucial for what we're going to discuss today, is that the theory is invariant quantum-mechanically as we move along a gauge slice, right? So this is a gauge slice, which in our case is a slice of all diffeomorphisms and Weyl transformations, right? Across Weyl. Right? And so what we were assuming when we were doing the next steps is that so once we choose a particular metric on this gauge slice, so we can so at this point, if you wish, and the path integral is invariant, whether we integrate with respect to this path or with respect to the g tilde, which differs from our gauge slice. And so what we showed, and I want to emphasize again that the whole symmetry on the gauge slice is a diffeomorphism invariant and Weyl transformation. And so when we did that, so we actually showed that path integral can be simplified. And so so now we can talk about this partition function as a functional of a fiducial matrix that is fixed. And so it takes a simple form, so it's an integral with respect to dx. And then we have a Faddeev-Popov rules. Faddeev-Popov determinant that came because of the gauge fixing, and we discussed last time extensively how this arises. And finally, we have a political action, which is a function of x and a gauge space method. So in other words, what we did to go from here to here, so we fix a metric, and then the integral over all possible metrics becomes the integral along this gauge slice, and so it simply cancels. If our theory has a symmetries quantum mechanically, that simply cancels the denominator. Okay, so very good. And next, what we discussed. So we went ahead and we tried to evaluate this Faddeev-Popov determinant. And we found a very neat formula for it, right? So I'm just going to write down the formula for this Faddeev-Popov determinant. So what we found is that the inverse of this Faddeev-Popov determinant, so that's a functional of G hat. So it's given by itself by a Cass integral. And this Cass integral is the Cass integral of E delta sigma. So we parameterized, we made infinitesimal parameterization of diffeomorphism group and Wald transformation. We have been able to integrate over infinitesimal Wald transformations, and we ended up with the integral d sigma. So this is the integral. Sigma here is a vector index, and beta is a rank 2 tensor. So beta prime equals to 0. So that's a traceless rank 2 tensor on the worksheet. And so this is e to the 4 pi I, an integral d2 sigma square root of g hat. And then I have beta prime ae p1 delta sigma of ab. Where P1 was just a differential operator on a worksheet. So let me see. I'll just write it down. So this P1 delta sigma of A. So it's simply 1/2 pi by A delta sigma E plus delta B delta B delta sigma Okay, so that's where we ended last time, right? And so you can see that in order for us to proceed, what we have to do, somehow we have to invert this relation because we evaluated the inverse of the Faddeev-Popov determinant, and the one that enters in the partition function is the Faddeev-Popov determinant itself. So that brings me to another side, and what we're going to discuss right now is, I'll give you a very quick introduction to Grassmannian calculus. So, intro to Grassmann calculus. So it's very simple. In fact, it's a Grassmann calculus, as you will see in a second. It's much more simpler than the ordinary calculus. So in ordinary calculus, we deal with variables, right? And those variables are Bosonian quantities. They commute. Okay? So you can extend the normal calculus by saying that you deal with variables which anti-commute. So in particular, so in Grassmann, if I talk about Grassmann variables, theta 1 and theta 2, so they anti-commute. And so when I try to change the order, I will pick up minus sign. So immediately, the consequence of the anti-commutativity of thetas is that theta squared equals to 0. Right? So if I take a square of this fermionic variable, I will get 0, which immediately tells you that the Taylor series expansions in this calculus are incredibly simple. So if I look at any function that depends on sigma, right? So this is arbitrary function. Okay, so I'm talking about a single variable function, and of course you can see how it can be expanded. Well, so the Taylor series expansion normally we write down as an infinite series. But what happens here is that this series expansion will always terminate, right? So what we will have is A plus B times theta plus nothing. Okay? So there cannot be anything else. Further terms in the series expansion precisely because what would have been here would involve theta squared and higher powers, and that's why it vanishes. So in order to build up calculus, we have to explain how do we differentiate and evaluate integrals with respect to Grassmann variables. And so those are the rules. Okay? So those are the rules how we do this integration. So d sigma, right? So d sigma. Well, okay. So let me start with differentiation first. So we define a differentiation with respect to theta in such a way that d over d theta of theta equals to 1. And of course, d over theta of 1 equals to 0. So now if I have two variables, theta 1 and theta 2, d over d theta 1, so this gives me theta 2, but d over d theta 2 of theta 1 theta 2. So it's minus theta 1 d over d theta 2. So in other words, d over d theta anti-commute with Grassmann variables itself. Okay. So we can write it down formally as anti-commutator. 0. So I explained you how to compute derivatives. So the last thing you need to note to have a complete calculus is how do you evaluate an integral. And so here, here are so if I have, so integral will have all the standard properties, right? And we're going to define d theta, the integral of 1, being equal to 0, and the integral of d theta of theta is going to be equal minus integral of theta d theta. So differential d theta anti-commutes, okay? So that's a minus sign here, and so this integral is equal to 1. So in other words, integration is the same as differentiation. In Grassmann calculus. Right? So again, those are the rules. So you have to when you start coming up, think of this as the axiomatics of your Grassmannian calculus. Okay, so any questions so far? Any questions? Good. So next thing. Okay, so the next step, we're going to do a trick that will allow us actually to convert a Dave-Loeffel determinant in the form that we would like to have it. And so I want to discuss two particular integrals, right? So what we're going to do, we're going to consider the integral so I have an integral over d psi, d chi. So psi and chi are my Grassmann variables. And what am I doing? I'm evaluating e to the lambda, the integral e to the lambda chi psi. Okay, so I'm going to evaluate this integral. Well, so what I can do a Taylor series expansion of this function. Okay? So this is an integral of d psi d chi, okay, and I'm expanding the exponential so that becomes 1 plus lambda phi psi, right? And that's it. Because, for example, the second term would be 1 over 2 factorial lambda chi psi squared plus higher order terms. Okay, and you can see that precisely because chi is Grassmannian, so the square of it must vanish. So this guy is 0 because chi squared will be 0, and all further terms will vanish as well. So, but that's kind of along the lines that I was telling you there, that any function of a Grassmann variables has a very simple Taylor series expansion, which is what we do here. And now we can just evaluate this integral. So this becomes 1 plus lambda phi psi. And so when we integrate 1, we have to look at our table of integrals. So this integral gives me 0. This is a constant. I have to pull it up. And then I have first the integral d chi pi gives me 1. And after I evaluate this integral, I can evaluate the integral with respect to psi. And so at the end of the day, I will have just lambda. Okay, so this fermionic integral gives me lambda. So the next thing we're going to do, we look at slightly different integral. So now I integrate from minus infinity to plus infinity of dx, the integral from minus infinity to plus infinity of dy, e to the 2 pi I lambda xy. Okay, so and here x and y are just normal variables. So those are just Bosonic variables. And so, so we can evaluate this integral. So this equals to, so well, I can compute the integral with respect to y first, and that will give me that will give me simply a delta function of lambda x if I integrate with respect to y. And so when I evaluate this integral, it's going to be 1 over lambda. Okay, so what we established with you, so notice that this integral is 1 over lambda, and this integral is lambda. So what we showed is that if we have a Bosonic integral of this type, okay, dx dy of type 2 pi I lambda xy, right? So this the value of this integral is opposite to the value of the integral when we go from Bosonic variables to fermionic variables, and in the exponential we move 2 pi I. So pi e to the lambda psi. Okay, so we found this very neat trick, how we can convert Bosonic integrals and get the opposite answer by rewriting them as a fermionic integrals. Okay, so now you can see. So the path integral itself is nothing but an infinite number of ordinary integrals. So that gives us an idea that so here we have an integral involving Bosonic variables, right? So delta sigma beta prime is the same as beta prime delta sigma, and so that integral, well, first of all, you can see that it involves 2 pi I times times some real kernel, something analogous to lambda, so the integral produces a Fourier-Pocock determinant to the minus first power. So we can take that integral and rewrite it using the fermionic variables precisely as we did here. And so according to what we just showed, the answer must give us the Fourier-Popov determinant itself, not the inverse. And so this is what I'm just going to write down. Okay, so what we're going to do, we're going to promote beta AB prime into BAB. So those are going to be our Grassmann ghost fields, right? So delta sigma sigma A, I'm just going to promote to CA. Those are our Grassmann ghost fields. Well, it's not exactly quite right because you can see that I actually have a factor of 2 missing somewhere, but doesn't matter in this definition, in this relation. So, so now, if this is the inverse of the Fourier-Popov determinant, then the Fourier-Popov determinant is the power plus 1 as functional of this fiducial metric. So I can write it down as a Fermionic class integral, EBBC, right? And so here I will have e to the minus s sub g, the action for the ghost, and so this ghost action here. This action as ghost equals 1 over 2 pi, right? And then I have an integral of d to sigma square root of g hat. So now you can see that I have beta prime, so I will have, well, so I guess the first thing I want to do here, I'm going to rewrite it with lower indices here and alpha indices here. Okay. So then when I move to a Fermionic integral, this will become BAB. And so here I will have P1 of P1 hat. Hat means that we evaluate this P1 with respect to a fiducial metric, C of A and B. Okay? All right, guys, so any questions? So you can see one place where I cheated slightly, right? So in order to use that translation that I wrote there, well, instead of having 4 pi, right, I should have 2 pi, and then there is an additional memorization of pi that I choose here. So in doing this translation, there are some, when I do this translation, there are some factors for the, for the 1 or whatever, pi or something. And you can figure out them exactly. But the bottom line is that we rewrite the bosonic integral in terms of d sigma and d beta in terms of the Fermionic integral involving Grassmann variables b and c. Okay? So any questions? No. Okay, so now if we go back, and ask what's P1, what's P1C is, right? So I give you an implicit expression. So what you will find out that this is simply nabla hat A on CP. Well, it's not quite true. So what is true in this statement? So in order for me to be able to rewrite this, I would have to kill, I think I erased the formula, which I wrote for P1. So we remember that this BAB is anti-symmetric traceless. So this is anti-symmetric traceless. Which the reason for that is because the starting bosonic field beta prime AB was anti-symmetric traceless, right? And so you can show that this once you contract P1CAB with antisymmetric traceless tensor, that's the same as contracting BAB just with a contravariant derivative acting on C. Okay, so good. Just, yeah.
Just BAB is just 4. It's consisted of 4 components, right? So 4 Grassmannian numbers.
Well, so A and B indices run. They are antisymmetric, right? Sorry, they run over 1 and 2. They are Wilshire indices, right? So in general, it's 2x2 matrix. So then all you have to do is to ask how many components the antisymmetric matrix has, right? So normally it would have so it's a little bit more than that. So it's antisymmetric traceless, right? So you just have a single component, right? That's an off-diagonal component.
Why is that antisymmetric? It's the same.
Yeah, actually, yeah, you're right. That's I knew I'm lying here. So it's not antisymmetric. Yeah, sorry. So beta is symmetric, but it is traceless, and it's enough for it to be traceless in order to remove a piece from here. So one of the pieces that is here was G hat AB, and that's a piece that we want to remove in the definition of P1 hat, and it will be removed once BAB is traceless, but it is symmetric. So which means that it has only 2 components, right? So
CA as well.
CA also has 2 components, right? All right, guys. So any more questions? Oh. Very good. So what did we do with you so far? So we've been able to write down the division function for single strings. In the following way. So it's division function that depends on a fiducial metric, okay? And so it's equal path integral. We still have to integrate with respect to dx. So notice that here is just the integral dx, and then we have a Faddeev-Popov determinant. But we wrote the Faddeev-Popov determinant as a path integral with respect to 2 fermionic fields B and C. So altogether we'll have dt dc, and then I have e to the minus sx minus the action for the ghost. Okay, so very good. So what we can do, we can now go into conformal. So let's go to conformal page. Conformal page, meaning that we're going to choose our fiducial metric as e to the 2 omega delta AB up to a y factor flat metric, and so now we have a very explicit expression for the ghost. So I can introduce sigma 1 plus I sigma 2 that are sigma 1 minus I sigma 2. And so the ghost action will be 1 over 2 pi, and integral over d2 that. So I'm writing down it instead of going, I'm going into conformal gauge, and I introduce conformal holomorphic and anti-holomorphic coordinates. So then this becomes B. That's that. I'll run that bar of Z. Okay. And then I have a plus bar. Okay, and so notice that it has exactly the right structure. Right, so this goes action was VAB, nabla A, CB. And so what I did here, I lowered the coordinate Z, then it becomes Z bar. And so here I lowered Z bar, it became Z. Okay. So the last step is, which I'm not going to do here. So, so in conformal gauge, so this is just a covariant derivative, and we can evaluate exactly what is this covariant derivative in conformal gauge. And it's just so happened that nabla of Z bar of CZ. So, so normally it has, of course, it always have del bar CZ, and then it might have a connection, right, a Christopher connection, and it just so happened that that in the conformal gauge, when I act on Kansas with an upper holomorphic indices, it will not produce me anything. So it's a simple exercise. Okay, so very good. So at the end of the day, our ghost action becomes 1 over 2 pi, and then I have d2z, bzz, del bar of cz plus bz bar del cz bar. Okay. Right, and so from now on, you should all scream at me and say, look, this is just a BC system, and that's it. So in fact, what we have here, we have 2 copies of BC system. So we have a holomorphic and anti-holomorphic system. So beta zz is d of z, and cz we call c of z. And bz bar will z bar, and c bar z bar. And so this is just as goes is well z del bar c plus tilde del c. Okay, so this is just a DC system. Notice, actually, what we have, this theory is conformal, right? So when I went to conformal gauge, you can actually follow through, and you will find out that it doesn't depend on omega, right? So it does not depend on omega, okay? And in general, so this is a conformal field series that we studied earlier with you. So in general, if we looked at the holomorphic BC system, right? And so the holomorphic BC system, in order for it to be conformal, so I have weights for B and C, HB and HC. So this guy equals to lambda and 1 minus lambda, right? So before lambda was anything, right? However, in this particular realization of the BC system, we know what is this B field is, right? In particular, we know how does this B field transform under conformal transformations. And so we already know what the holomorphic weight is. And the reason why we know is because what we call B in the BC system is actually a B field with 2 lower holomorphic indices, right? So what this tells us that HE must be equal to 2, and HC equals -1. So the reason it's -1 because it has a holomorphic index upstairs instead of downstairs. So in other words, so when we went ahead and did the gauge fixing in Quadratic path integral, we found that we have a ghost BC system, and not any ghost BC system, but ghost BC system precisely with lambda equals to 2. Okay. So so any questions so far? Okay. All right, guys. So now we have to go ahead and see is there any problem with what we did. And of course there is, because we have been swapping. I have been swapping. So where's the problem could be, right? So remember, I was asking you last time when we were breaking the path integrals with respect to the gauge orbits and gauge non-equivalent configurations. I was asking what's the implicit assumption, right? And you all told me that the implicit assumption was that path integral expectation function, right, should not depend, since we are assuming that diffeomorphism invariance and while invariance are symmetries, right? So we evaluated it using a specific metric, but at the end of the day, if we have the symmetries that we assume that we have, so this expectation function must be invariant. It must be exactly the same, even if I choose a different fiducial method. So in other words, if I have the path integral with respect to gauge inequivalent configuration, right, meaning that each trajectory intersects a gauge slice once, right? So on this trajectory, I have g hat. So the answer for the path integral must be the same if I choose a different trajectory by simply acting with diffeomorphism or Weyl transformation. So clearly, so diffeo times Weyl is a classical symmetry. Of Sx and Sg, right? So we ended up having Quadratic action for the X field, and we got a DC system. And those two theories have, diffeomorphism and Weyl invariance classically. But we're talking not about the invariance of classical actions, we talk about invariance of the partition functions. And so the questions that we must ask is, does this symmetry survive quantum mechanically? Okay, so is diffeo times Weyl a symmetry quantum mechanically? Okay, and I'm just gonna go into some general discussion and tell you that that's actually a highly non-trivial state. Okay, and very often, so first let's talk physics, then we'll talk about technical aspects, where exactly the problem will come at technical level. So, so in particular, one of the elements of the Weyl symmetry group is just rigid rescaling. Okay, so the series is scaling better. So let me look at this series. So I'm in 4 dimensions. 4 space-time dimensions. And so I have minus del mu. I have a simple scalar field, del mu 5, right? And then I have plus lambda 5 to 4. Okay. So I look at this theory, and so this theory is classically scalar invariant, right? So classically, and the reason for that is that, well, remember that the reaction is E for L, right? E for X of the Lagrangian density, right? And so Lagrangian density must be a dimension 4 operator. So on my scalar field is dimension 1 operator. Del is dimension 1, so you have a dimension 4, you have a dimension 4 operator here, and the mass dimension of lambda equals to 0. So classically, our theory is scale invariant. But you all know that that's misleading, right? So if it would be scale invariant, then this statement would be correct. D over d mu of lambda must be equal to 0, where mu is the energy scale. And you know that it's not so, right? That's exactly what gives you the beta function for lambda, right? So this is proportional beta function corresponding to the Kaplan lambda. Okay, and so this is the simplest and most trivial example, I would say, in which you have a theory where you have classically scale invariance, but the scale invariance is broken in quantum field theory. Okay, so now you go ahead and you ask, where at the technical level, where exactly the breaking occurred? Can somebody tell me? It's too complicated. But sorry?
Introduce the cutoff.
Right. So that's the point is that when we start computing quantum corrections, there will be divergences, right? When we just evaluate loop diagrams. And so what we need to do, we need to regulate these loop divergences. And the problem is that it's very difficult. We can introduce a cutoff, which is Lorentz invariant. That's what we do usually. Well, I mean, that's what we do in relativistic quantum field series. But it's not possible to introduce a cutoff that scale invariant. So the cutoff will break scale invariance. And so that's through the introduction of this cutoff, eventually the scale dependence creeps in. So this is known, okay, I'm not going to go into all this discussion of dimensional transmutation and all that stuff, but at a technical level, the breaking of classical symmetries come because typically quantum corrections will produce divergent result, and you have to regulate this divergent result, and the point is that you cannot regulate it while preserving the classical symmetries. Okay? So another example, which is of the same kind of type, is the Yang-Mills theory, right? So
Let's finish dimensional integration. Then all.
Well, there is in dimensional regularization, since you have to go away from 4 dimensions, you have to introduce scale as well. Right? So there is your regulator explicitly introduces a scale as a whole. So the whole point, one of the points that this theory is scale invariant because there is no explicit scale. Right? So so what will happen if you do two-dimensional regularization? The integral will not be with respect to d, but with respect to whatever d minus epsilon, or whatever how you parameterize d minus 2 epsilon. And once you do that, then this coupling will not be dimensionless anymore. It's dimensionless only in 4 dimensions. So dimensional regularization is n, and one of the examples that will break scale invariance. Okay. All right, guys. So another example, and this one was very famous because once people realized it, people got Nobel Prize for it, right? And so that's a non-abelian Yang-Mills theory, right? So if I talk about non-abelian Yang-Mills theory, so the Lagrangian takes the form minus a quarter f mu, that is f mu equals del mu and mu minus del mu and mu and plus g, and I have a commutator in mu and mu. So again, what you have here is that canonical dimension of the vector field is +1, and so f mu has a canonical dimension +2. So you can see that your Lagrangian L has a canonical dimension +4. So in particular, you see that the gauge coupling is dimensionless. So a non-abelian Young-Mills theory, you knew this fact, but you probably haven't appreciated it before to full extent, is actually scale invariant classical. Okay, but again, this classical scale invariance is broken by quantum effects because you know that d over d mu of g squared of mu is not equal to 0. Again, it's related to a famous beta function in non-abelian gauge schemes. So those are all the examples in which you have classical symmetries, and those classical symmetries, in particular, I'm speaking about very concrete symmetry, which is scale invariance, is broken by quantum corrections. And so it should not be a surprise to you as well that, look, so here we are talking about the two-dimensional quantum field theory on the world shape, and we're assuming that it has scale invariance, but that scale invariance can be broken. So what we're going to do right now, we're going to actually do a fairly precise computation and understand how that scale invariance can be broken. We will talk the reasons why we don't want it to be broken. Okay, so and after that we will again discover our favorite critical dimension. So we'll find out that insisting on conformal invariance of the world shape, particularly invariance under Weyl scalings on the world shape, will tell us that the string theory can consistently propagate only in 26 dimensions. Okay, so that's our goal. All right, guys. So let's go ahead and move. So any questions? Okay. So what we want to do, we want to, so I have to apologize, some signs might be at some factors, I might be off, but hopefully not too much. Well, first of all, classically, what do we have? So we have that bullshit stress energy tensor is given by this expression, 4 pi over root g, and then variation of the action, delta GAD. And so in particular, this tells us how does our action varies when we vary the metric. And so delta S equals to root g over 4 pi, root g over 4 pi, and then I have delta GAD, TAD. Okay? So now we can ask the question. So again, the logic here is following. So in relativistic quantum field theories, I told you that the breaking of classical symmetries occurs because there will be divergences when we compute loop corrections. And that, in turn, comes because it's difficult to come up with a regulator that preserve classical symmetries. So much like in quantum field theories, it is possible to have a regulator which will preserve diffeomorphism invariance. Okay? And so the only issue can arise, or the only anomaly can show up in Weyl transformations. So what we're going to look, so diffeom is okay quantum mechanically. And the reason again, we can use compute loop corrections. And the only problem can come, so only problem can come from Wald transformations. Okay. So, so what I want to do, I want to evaluate a path integral. I want to ask, how does my path integral changes? So we want to ask, if I do Wald transformations, how does, on the metric, how does my partition function changes? Okay? So that was the fiducial metric. I will stop writing it, and by that I simply mean that I took a fiducial metric and I made a Wald transformation on it. Okay? And I want to know how does a partition function of the string theory of a Polyakov string changes as I use this Wald transformation. So actually, we can be more general, and so instead of talking about a partition function, we can talk about a path integral involving arbitrary insertions, right? And so, in other words, what we will be interested in? We will be interested in. Suppose I have some insertions, I prepare some state inside this path integral, and I'm asking that. The Wald transformation of a path integral with insertions vanish. So this is a strong statement. So, and I'm doing Wald transformation around certain fiducial metric. And so at the end of the day, we want to have 0 because we want our Wald symmetry to be preserved for them mechanically. So if we want exact Wald symmetry. Okay. Good. So you might ask me, why do we want to have exact Wald symmetry? And I'll go back to that after we do all the technicalities and evaluate conditions when we will have it. So let's for now take it that there is a need for us to preserve Wald symmetry of Polyakov string. And so let's see what requirements does it impose. Okay, so here if I have a variation, so this is a path integral, right? So this is the guy that involves dx, right, e to the minus fx, with possible insertions. And so I'm varying with respect to metric. So the term, I have to look at the term, I will concentrate on the term due to the variation of the action, right? And on this blackboard above, we relate the variation of the action to the variation of the metric times the stress energy tensor. And so what I can write down is that the variation with respect, well, actually here, I'm going to write down variation with respect to arbitrary metric delta G of a path integral with insertions. So this is minus 1 over 4 pi, and the integral will reduce to sigma, and then I have square root of G, okay, and delta G. And then I have an expectation value, right? So there is a, if I vary with respect to metric, so metric enters in here. So there will be TAB, and then there are whatever insertions I have. Okay, so that's a general formula, right? And now we look not at the arbitrary variation of the metric, but variation of the metric due to wild transformations. Okay, and so in that case, delta G, the variation, the metric varies as 2 omega times GAB, right? So under wild transformation, the metric simply rescales. So delta GAB is simply, well, I can write it down as 2 delta omega. Which one? Yeah, I use delta omega. 2 delta omega GAB. And so the variation of Hess integral with insertions with respect to wild transformations will be simply minus 1 over 2 pi. And then I have an integral e to sigma square root g delta omega GAA evaluated with respect to some fiduciary metric above which we're doing the wild transformation. Okay, so is it clear? So the condition that everything I compute in this theory is invariant under wild transformation means that I put 0 on the left side. And so what this means that as an operator statement, the stress energy tensor must be traceless. Okay? So this statement is trivially, we obtain this statement trivially for the X theory, right? Or for the BC theory by classically by evaluating the stress energy tensor. But the point that I'm making here is that actually this statement must be true, including all quantum corrections, right? So this is true as an operator statement. So in other words, the signature of gradient scale invariance will show up that the trace of the stress energy tensor quantum mechanically is not equal to 0. Okay, so this is our left-hand side, and this is right-hand side. Okay, so while invariance is broken, on the right-hand side is not 0. So the only thing to do here would be something what you guys did in lambda phi to the 4th series, right? Just find out, regulate the computer loop correction, and see what are the conditions, right? So something like what is the conditions that the beta function would vanish. So what we're going to do, we're going to take a different approach, something that doesn't require directly to do any massive loop computations. Right. So what we're going to do, we're going to guess. Okay, we're going to guess what can be on the right-hand side. Again, the idea is we're assuming that we're going to do exactly the same steps as we are doing in lambda phi to the 4th series. And so what we would like to do now, we want to ask the question. So suppose it's not 0. What it can be, right? If it's not 0. How can we fix what can be there? Well, we have to ask the question, what are the symmetries? What is allowed by the symmetries of the problem? Well, first of all, I claimed without proof, but it can be justified, is that that we can introduce regulator which is diffeomorphism invariant. So whatever is question marks here must be invariant under Lorentz diffeomorphism. Right? That's the first point. So the second point is that, well, the stress energy tensor has some scaling dimension. Okay, so the scaling dimension on the left-hand side must be the same as the scaling dimension on the right-hand side. Okay, so scaling dimensions on left-hand side must be equal to scaling dimension on the right-hand side. So in other words, our strategy is to use, if you wish, dimensional analysis to try to guess what are the possible operators we might have here. which are invariant under diffeomorphism transformations of the wall shape. And so we will determine a bunch of such operators up to a set of coefficients. And then our task would be to actually compute those coefficients. Okay, so that's what we're going to do. So, let's look at action for X fields. Right. So what do we have? So let me write it down one more time. So it's 1 over 4 pi all the time integral into sigma root g GAD del AX del DX. So I'm going to use worldsheet units. Okay, and so if I'm going to use worldsheet units, so in this worldsheet unit, the dimension of X equals to 0, right? And the dimension of GAD equals to 0. So in other words, what I'm using as my units the lengths on the worldsheet. Okay, that's not the same as this alpha prime, which is the length of the string in a space-time. Okay, so that's why I can use, that's what I'm saying is that I'm using a worldsheet unit. Okay, so dimension of X is 0, dimension of the metric is 0, but dimension of sigma 1 or dimension of sigma 2 equals to -1, right? So those are just lengths. So they have -1 unit in terms of scale, right? And so derivatives del A is +1. Okay? So is it clear? In particular, E sigma A. So my action is dimensionless. Okay? Again, I'm just using a dimensional analysis to figure out what's the dimension on the left-hand side. So what's the dimension of TAB? Yeah, just one second. So TAB, yes.
Should the Einstein equation directly tell us what's going to be Because everything happens in curved space-time, and that's the only dynamic.
Right, but okay. So first of all, by Einstein equations, you mean Einstein equation in the space-time, right?
Yeah.
So at this stage, we don't know why do we have Einstein equation to begin with. Okay, we will talk about that maybe if we'll have time today. How does Einstein equations are being derived? See, that's something that we don't want to put in string theory. We don't want to put by hand a graviton, and we don't want to put Einstein equation. One of the beauty of the string theory is that it will come up automatically. Okay, and that's what I'm going to show you how it will come up. And the way it will come up is precisely related to the subjects that we are talking about by asking the question, how do we preserve classical symmetries that we have and how we insist that those symmetries are quantum mechanical? It's exactly what we would see is that insisting that, in particular, this wild symmetry is exact quantum mechanically will give us Einstein equation, okay, in curved spacetime. But for now, we don't know it. And we don't know Einstein equation. We don't, and what we're doing really two-dimensional quantum fields here. We're asking the question, okay, we're going to compute loop diagrams, there will be divergences, but we're taking shortcuts. We're asking what kind of operators can show up, okay? And so the way to sort this problem out, as I was saying, is to use worldsheet dimensional analysis. And from that, we conclude that the dimension of the stress energy tensor is +2. Okay, that's +2 on a worldsheet. And the reason is because the stress energy tensor is del x, del x. There are two dels, and each del has a canonical dimension +1, so the stress energy tensor has a canonical dimension +2. Okay, so again, this is just plain dimensional analysis, and so also quantum mechanically, In other words, it's units, okay? Even if you include quantum corrections, a meter cannot turn into a meter squared. It must still be a meter. So analog of this Wiltshire units is kind of analog of a meter. So what this tells us that even including quantum corrections, the final corrected, regularized, and renormalized Wiltshire stress energy tensor must have Wiltshire dimension +2. And so then we are asking the question, so what kind of operators we can write down under this question marks, which has a dimension +2? And those operators must be diffeomorphism invariant on the Wiltshire, right? And be some local operators, right? So we're talking about local quantum field theory, and we're talking about local regularization and renormalization. What we are assuming here is this two-dimensional quantum field theory can be renormalized. And the answer to that question is yes, but that's something that I'm not going to prove to you. So assuming that it can be renormalized, which means that the trace of the stress energy tensor renormalized and regularized, regularized. Well, first you have to regularize it. But actually, for now, I'm just regularizing it. I'm just introducing a cutoff. Okay, so the cutoff is explicit scale that will break scale invariance. And so whatever I write down here must be a dimension 2 operator. Well, so one thing I can write is A1 times a curvature on the Wiltshire, right? A curvature on the Wiltshire has two derivatives of the metric, two Wiltshire derivatives. Because it has two Wiltshire derivatives, the canonical dimension is +2, and that's why it can come up here. Another thing, there might be a coefficient alpha, right? And well, so notice that here I'm talking about the trace of the stress energy tensor. So it must be an object which is a scalar on a Wiltshire. So I have to contract all indices. So one thing that I can write down is this one, okay? Just something that has two derivatives, right? So this is a dimension 2. So it has two, again, two derivatives, and so this is a Wiltshire dimension 2 operator. And in principle, as long as I'm talking about regularized stress energy tensor, so I introduce the cutoff, so there can be an infinite set of additional corrections. So I'm going to write it down some n equal 1 to infinity. So this is a scale, mu sub n. So I'm just saying that the Wiltshire units of mu is +1. And then here I have 2 plus n. Okay? Right. So the reason I'm doing it this way, so I'm not introducing the negative powers of mu, because I'm assuming that the theory for my next step, assuming the assumption that the theory for a correction, for a constraint is, as a two-dimensional quantum field theory, is a renormalizable QT, that the theory is renormalizable, which means that it must have a well-defined answers to physical questions as I remove the cutoff to plus infinity. So as I remove the cutoff to plus infinity, so all these terms will become irrelevant. And so the only two terms that can come up, okay? So that's, if you wish, a quantum regularized stress energy tensor, TAP regularized, which is the same as quantum. Can only depend on two constants, A1, A plus alpha del x squared. Okay, so that's the only two things that can show up if we include all quantum corrections. Okay? So what do we know? So the particle string is Sx plus S ghost, right? And so those two actions, Sx and S ghost, those two actions are conformal field series. Conformal field series when metric GAB equals delta AB, right? So when we have a unit metric, so remember we define our conformal field series with a flat metric in 1 plus 1 dimensions, right? And so because they are conformal field series, so the stress energy tensor, when they are conformal, must be equal to 0. And so what we have to conclude that and by here I mean including all quantum corrections, right? That's what we studied a lot about conformal field series, and we showed that the trace of the stress energy tensor vanishes in conformal field series. So here we have a condition that this quantum TAA must vanish when the metric is delta EB, right? So when we have a flat metric on the whole sheet, then the trace of the stress energy tensor must vanish. But when I have a flat metric on the world sheet, that implies that R equals to 0. So we have a condition that TAB, when R equals to 0, must be equal to 0. Okay? So that tells us that even though naively there are two dimension 2 operators that can enter quantum mechanically, the fact that the theory is conformal with a flat metric implies that this coefficient is 0. In principle, it didn't have to be 0. And so what we used here, we used our knowledge of CFT and the fact that in that limit, the series that we talked about are conformal field series, to conclude that actually, once we would do the loop computations, the beta function for that coupling alpha would end up being 0, would produce 0. So what we discovered with you is that for the particle action, the only thing that can happen is that the trace of the stress energy tensor is going to be equal to A times R, where R is Ricci scalar on the wall sheet. All right, so any questions so far? Good. So the next step is we're going to explicitly compute this coefficient A1. So A1 is just a number, and we're just we're gonna evaluate this number. All right, good. So, we know TAA equals A1R. What this tells us, T ZZ plus T Z bar equals to A1R. Well, what I can do, I can lower the indices to T Z bar plus T Z bar Z, which is twice. It's a symmetric tensor, so this is just twice T Z bar in one R. So from that, okay, so I'm cheating a little bit. So there is also the metric. There is also the metric. G. G. And so say Tz at bar is 1/2 A1R D bar. Okay? So that simply follows from the condition TAA equals A1 times R. So now I'm just going to evaluate this covariant derivative. So I'm just going to evaluate del z bar to z bar from that. And so this equals to A1 over 2 del z bar. And here I have G that's z bar, which is K. Okay? So we always make our covariant derivative with respect to Levi-Civita connection, which means that the metric is covariantly constant. So this guy is simply A1 over 2 Gz z bar, and I have nabla z bar active on part. Okay, so which is the same as A1 over 2. So what I'm doing here, I'm lowering the index of nabla, and so that simply becomes nabla z of R. Now, usually, this is a covariant derivative, right? And so it involves a simple derivative plus, again, connection. But connection is non-trivial only if it acts on tensors, right? So if it acts on scalar, it doesn't matter. And so this simply becomes A1 over 2 holomorphic derivative. Sorry?
Are you conformal gauge?
Well, right. So I am in a conformal gauge, right? So the whole point was to be able to do wild transformations.
Yeah,
right? And so in a conformal gauge, I can still do wild transformations.
I mean, what I meant is if this arbitrary metric, this Gz as a bar doesn't lower that. You have to be in conformal gauge that.
Well, I must be in the metric in which I can introduce holomorphic and anti-holomorphic. That's correct. Yes. Yes. Okay. Good. Very good. So. Now, one of the things that we are using is that if the workers invariance is not violated by quantum effects, and so if the stress energy tensor is invariant under Bolshevik diffeomorphic transformations, well, that simply implies that nabla A T equals to 0. So our stress energy tensor must be covariantly constant. So this is the same as nabla bar. Nabla z bar of T z bar z plus nabla z. So guess what I'm doing is okay, and it must be equal to 0. So what we evaluated was U up here, right? So we evaluated that. This guy equals to A1 over 2 del R, right? And so what we are finding nabla z T z must be equal to minus A1 over 2 del R. Okay, so this is a relation. That that we're gonna test. So far, this relation is correct in a conformal gauge, right? What we want to do, we want somehow to compute this A1, or more precisely, what we will do, we will relate the A1 into a conformal anomaly, right, into a central charge in our CFG. And so in order to do this, so we have left-hand side and we have right-hand side. And so we just did some manipulation where we have an equality. And now we're going to add with wild transformations on the left-hand side and on the right-hand side. Okay? So what we're going to do, we add with wild transformations. On the left-hand side and on the right-hand side. And so the reason why we you can see the logic here, why this will allow us to fix A1. The reason is that when we do a Weyl transformation, I can still stay in a conformal gauge, so I can relay a Weyl transformation to a particular type of conformal transformation. And I know how my stress energy tensor transforms under conformal transformations, right? So it will transform as a rank 2 holomorphic, as a weight 2 holomorphic tensor, plus there will be a conformal anomaly. So we will know exactly how the left-hand side transform under Weyl transformations. And we also know, and this transformation will depend on the central charge, right? Now, the right-hand side, this is simply a Weyl transformation on the metric. So I know how does my Ricci scalar on the wall sheet changes when I do Weyl transformation. And so by relating Weyl transformation on the left and on the right-hand side, I will be able to relate the A1 to the central charge of the CFT. So is it clear logic? Because I don't want, we can get lost all in the computations. Okay, good. So let's go ahead and let's do Weyl transformation on the right-hand side. So that's a bit simpler for us. And then we go and look at the left-hand side. Okay, so to get the point, we do this Weyl transformation, and we're going to look first at the right-hand side. So what we have, our metric GAP goes to GAP prime, which is e to the 2 omega GAP, right? And so something that we used previously many times is the formula from Wald, which tells us how does Ricci scalar transform. So square root of G prime or prime is going to be equal to square root of G, and here I have R minus 2 nabla squared of omega. Okay, so that's a Weyl transformation of Einstein-Hilbert term on the wall. Okay, so what we're going to do, we're going to do Weyl transformations about GAP equals delta AD, right? So we're going to do our Weyl transformation very close to a flat metric on a wall sheet. And so in that case, R will be equal to 0, right? So in this case, the untransformed one is going to be equal to 0. And so this R prime is going to be equal e to the minus 2 e to the minus 2 omega, right? So the original Ricci scalar is going to be equal to 0. So I have minus 2 alpha squared of omega. Okay. Now we are interested. So we want to know how does and so this is the same. I can write down R prime minus R, right? And this is the same. How does my Ricci scalar transform? I think maybe it's better if I put delta omega here as well. So I'm asking how does Ricci scalar transform about flat wall sheet to linear order in delta omega? And the answer is minus 2 nabla squared delta omega. Right? So this is the transformation on the wall sheet Ricci scale. Okay. So very good. So so now let me go ahead and okay, so we'll be back. So this our identity left-hand side equals to right-hand side. So what we discovered is that the Weyl transformation of the right-hand side is going to be equal, so I have -2 times -a1 over 2. So that's going to give me a1 del number squared of delta omega. Okay? So we would like to do exactly the same with the left-hand side. Okay? But before, let me write it down in terms of holomorphic and anti-holomorphic coordinates. So remember that del is just 1/2 del 1 minus I del 2, and del bar is 1/2 del 1 plus I del 2. And so this number squared is del 1 squared plus del 2 squared. So I can rewrite this in terms of del and del bar. So this is the same as 4 del bar. And so the final formula here, so this guy, is going to be equal to 4 a1 del 2 del bar delta omega plus corrections of 4 there. So we neglect higher order terms, right? So we neglect quadratic terms. Okay, so any questions so far?
Why you cannot ignore the quadratic term?
Right. In principle, you don't have to, and you can do. But I'm saying I'm looking for the fastest route to get to the answer. And so there will be higher order terms as well. I'm not going to neglect them. But what we will see on the left-hand side, there will also be a linear term. And so if we have an identity of that type, it must be correct to any order in a Weyl transformation. So if it's enough for me to look at the linearized order, that's good enough, right? And that's exactly what we're going to do. Remember that what we are doing right now, we are trying to avoid the quantum mechanical computation of group diagrams with discussing all the issues of regularization and renormalization and all that stuff. And we try to find out the fastest way to the answer, okay, without doing any hard work. Okay, so let's do the same. Let's look at the left-hand side now. So when I do conformal transformation, okay, with some parameter epsilon, so my stress energy tensor will transform. And we know exactly how the stress energy tensor transform. So there will be minus C over 12, right? Del 3 of E, right? So here, what I am saying, I'm saying that I'm doing a transformation delta Z equals epsilon B of Z, right? Where epsilon is my infinitesimal parameter, and delta Z bar is epsilon B bar. Right? So the holomorphic stress energy tensor TZZ transformed minus C over 12, the third derivative of B. And so this is an anomalous term. Okay. And then there are two more terms. Del B TZZ, and then minus B del Z TZZ. Okay, so so this transformation that we actually always thought as being trivial, right? So those are just due to coordinate transformations. If I have, I don't know how I'm gonna, if I have any tensor M, okay, so if I would really have a primary field with two local holomorphic indices, then it would transform under coordinate transformation precisely as the last two terms of the stress energy tensor. Okay, so this piece up here, we never discussed what is the physical origin or what is the physical reason that this piece shows up. And what I wanted to say is that, well, we have to see what kind of transformations are happening when we do these conformal transformations, right? So, so remember that a metric on the wall sheet was dz bar, and so now we made conformal transformation, and I want to ask the question: what would happen with the metric on the wall sheet under conformal transformations? And so you can see that I have d z plus epsilon b, right, and then d of z bar plus epsilon b bar, if you wish, right? And so what you can see that this is the same as dz bar, and then I have 1 plus epsilon del omega plus epsilon del omega bar. Right? So what I want to sell to you is that, look, when we make a conformal transformation, what will happen is that our metric does not stay invariant. So there is a wild transformation acting on the metric. Okay. And so in other words, we actually talked a bit about this before, but so conformal transformation, when z goes to some function of that, is actually equivalent to coordinate transformation plus while rescale. Okay, and so in particular, just by looking how does my metric transform under conformal transformation, I can see that the Y factor 2 omega must be equal to epsilon del E plus epsilon del bar. Okay, so we have accompanied Y transformation as well. So now this anomalous term, the right way to think about it is that when we make conformal transformations, there are two types of symmetry transformation that occurs. One is coordinate transformation, and that's those, it will produce those two terms. And then there is one leftover term. And so you should say then, well, you know, since the symmetry transformation that you did involves also a Y transformation, what that implies that under Y transformation, the stress energy tensor will transform, and it will transform exactly as dictated by that first term. So how do I write it down? Well, so it must be that piece, so it's minus C over 12 del 3 of E times epsilon. Okay. And now I'm going to write this down as minus C over 12 del of del 2 of epsilon del E. Okay? And I'm just going to add anti-holomorphic part. Okay? That's not going to change anything because our conformal transformation breaks into holomorphic and anti-holomorphic parts. So this guy is anti-holomorphic. So if I keep it with a holomorphic derivative, it will vanish. So I haven't done anything. But now I know that this combination here is exactly twice delta omega, right? So this is twice delta omega. So what we discovered is that by carefully looking at the transformation properties of the stress energy tensor under conformal transformations, we identified how does our stress energy tensor transform under Y transformation. And so that's given by, there is a factor of 2 here. So I have minus C over 6. And then I have del 2 of delta omega. So any questions? All right, guys, so we're done, right? Because now we can answer the question, how does the left-hand side of that equality, and of course there is a higher order term here, which I'm not going to write. We can ask, how does our right-hand side transform under Weyl transformations? And so, Weyl transformation of the right-hand side of our identity. So, well, I have minus c over 6, right? Minus c over 6. C is a constant. And then I have to act on it with nabla z. Nabla z on del 2 of delta omega, which is minus c over 6, del r, del square of delta omega. Okay, and then there is a higher order term in principle. We never get that. Okay, so if the left-hand side equals to the right-hand side, then of course delta omega of left-hand side must be equal to delta omega under Weyl transformation of the right-hand side. And so it must be the case that c over 6 del bar del squared of delta omega must be equal to something that we evaluated before, which was okay, did I see?
Well, you have 2 delta bars.
Where?
In the second equality.
No,
The delta
it's not
square.
delta 4. Sorry. I'm off by a factor of 2. I'm trying to. Okay, so that guy. So this is minus 6, and this is correct. So I have minus 6 del bar del squared delta omega, and on the other side we have 4 A1. Okay, and so I'm off by a factor of 2. So from let's see if I can work this out. But first, notice that there is a non-trivial fact that the dependence on a particular form, even if it's linearized form of the Weyl transformation delta omega, is exactly the same. Okay, and so that allows us to fix in 1 and in 2. And so what I'm finding.
When you lower the z, you miss the 2.
Upper and lower.
So right, yes, thank you. So you're absolutely right. So it wasn't a matter when I was lowering, forgetting about, yes, there is GZ, there is a factor of 2. Yeah. Great. But it didn't matter in anything I said before because, but it matters. Thank you. Great. And so, so now you can see that we compute that A1 is actually minus C divided by 12. And so our conformal anomaly, the trace of the stress energy tensor, is related to a central charge, which is with a very specific coefficient, C over 12. Okay. Good. So any questions? So I'm going to say a little bit more words about this in general, right? So conformal anomaly, right, so where does the central charge shows up, right? So how do you, if somebody will give you a theory which is, well, I mean, scale invariant, for example, classically, and you want to compute conformal anomaly, right? So in other words, you want to compute this central charge. So you see immediately that you will not do, you will not be able to extract the central charge. In some sense, what we're computing here, we're computing a one-point correlation function of the trace of the stress energy. So as long as you compute that one-point correlation function in the flat space-time, you will always get 0, right? So, for example, you'll often get 0, right? And so it doesn't mean that you will not be able to see this central charge. So what we are talking now is how do you what computations do you have to do in quantum field theories in general in order to be able to extract the central charge? And I'm saying that as long as you do computation in flat spacetime, CFT in flat spacetime, then you cannot extract central charge from a one-point correlation function. Okay? It doesn't mean that it's not impossible. So what you have to do, you have to look at the two-point correlation function. So if you look at the two-point correlation function, here at some point x and here at some point y, there will be a characteristic singularity which depends on the space-time dimension. And what will happen here in this correlation function, it will be proportional to the central charge. So this is computation in the flat space-time. Okay? Flat space-time. So you can extract the extract the central charge if you do a flat space CFT analysis, as long as you look at the higher point correlation function. So this information encoded in a higher point correlation functions. Typically, those things are more difficult to compute. The lower point correlation functions are easier to compute. But then you see here that you can compute a central charge by simply looking what the theory looks like, or computing the one-point correlation function in curved background. Okay, and so what I want to end here this talk here with an example of the unequal force supersymmetric Yang-Mills. Unequal force supersymmetric Yang-Mills. So you can ask exactly the same question. So the theory is scale invariant classically, right? So well, it's conformal theory, but it has a central charge. Once it has central charge, there will be there is a non-vanishing C. So how do you compute it, right? And so one way to do it, as I said, you look at this unequal force supersymmetric Yang-Mills theory in flat spacetime, and you look at the two-point correlation function of the stress energy. That's a difficult computation. But the simpler computation, you can do exactly kind of parallel to the analysis we did for the cortical string. So you look at the one-point correlation function of the stress energy tensor of the theory in a curved background. So if I have a background in which, say, A, B, C, D, the Riemann tensor is not equal to 0, then the trace of the stress energy tensor is actually, I'm not going to write down the exact coefficient in front, but it is proportional to the central charge. And here you have RAB minus 1/3 R squared. Okay? So you can see that, again, you can get the information about the central charge of the system, which is a crucial information. It tells you number of physical degrees of freedom, right? It can be encoded in the central charge of your theory. And so you can extract that vital information just by looking what is the one-point correlation function of the stress energy tensor in curved background. Okay? And so I'm saying that in this context, it gets a very specific combination. There is, well, I cannot not mention this. Yeah, sorry? No. One thing that you notice here is that so this guy vanishes, right? So this guy vanishes when we look at the theory flat spacetime R3, 1, but it's also vanished. When I look at the theory at R cross S3. It just so happened that this factor 1/3 between the square of the Ricci and the square and the Riemann, or the Ricci and the square and the Ricci scalar is precisely such that the conformal anomaly will also vanish when you evaluate in this four-dimensional field theory on R cross S3. And you can ask, what is the reason for that? Well, you can think of that, well, actually the map, you can make a map between one and another. And this map is exactly the map as in the case of the Polyakov string going between a cylinder and a plane, okay? So that's a map which relates operators on one side with states on the other side, okay? So in other words, the states of the theory on R, 1 are the same as operators of this theory on R cross S3. And that's part of their conformal symmetry group. And that's why, much like, yeah, well, so in n equal 4, it doesn't show up. All right, so very good. So let's talk, let's finish discussing about how do we cancel this conformal anomaly, and then we'll discuss what will happen, well, I just mentioned briefly after the break, if we don't cancel this, right? So what we are finding that a Polyakov string is anomalous unless, so Polyakov string is anomalous unless the central charge equals 0. So in the case of the Polyakov string, we have two contributions to the central charge, right? So there is a central charge coming from the X system, and then there is a central charge coming from the ghost system, right? So the central charge for the X system we computed with UD4, and that's simply B, because we have B free scalar fields in a conformal gauge on a worldsheet, so it has a central charge of B. So here, what we have a DC system in a conformal gauge with lambda equals 2. And something that I told you, we'll come back to that, it will be important, is that precisely for this value of lambda, the central charge is equal, so the central charge is equal to minus 26. So what we are finding that the central charge of the Polyakov string, in order for it to vanish, the Polyakov string must live in a critical dimension p equals 26. So this is a different way how we derive a critical dimension for the string, right? So remember, we derived a critical dimension for the bosonic string in a light cone gauge, right? So we impose light cone gauge. We explicitly broke Lorentz invariance, right, in the spacetime. And the computations that we did here does not break it. So this way of deriving a critical dimension actually is entirely Lorentz invariant. In fact, if you think back then, how did we get the critical dimension in a light cone gauge? So we noticed that the light cone gauge will break Lorentz invariance, and then when we insisted that we do have Lorentz invariance, that gave us the critical dimension, right? So there, well, which arguments is better, it's hard to say. I mean, they are very different and they rely on different underlying reasons. So, all right, guys, so what we're going to do, we're going to take a like 10-minute break. And after the break, we'll discuss why do we need, well, maybe a little bit later, but we'll talk in general about scattering amplitudes in the Polyakov string.